Yes, you're all very, very welcome for that. And since I got applause earlier, I'm also retired a few years ago, and I've come back to UT to work on my degree in astronomy. And I think maybe I'm the oldest graduate student we have. Maybe yes? I am now? Yeah. I am Dustin Davis, and also known as Lyman Z Coconut. And tonight I want to talk to you about the mysterious Lyman-alpha blobs. Now back in 2000, Charles Steidel and others were conducting a survey of distant galaxies, looking for star formation and galaxy formation rates. And they noticed some weird, irregularly shaped, glowing clouds that seemed to be surrounding some of the galaxies that they were looking at. And they named these weird things because of their odd shape and the fact that they glowed in Lyman-alpha, Lyman-alpha blobs. Now they named the first one Lyman-alpha blob 1 and the next one Lyman-alpha blob 2. And if you're very, very clever, you can probably figure out what they called the next few dozen that they found. Now when you encounter something brand new and unexpected, you try to learn everything you can about it, and you ask a series of perhaps obvious questions to try to understand the objects in more detail. So you might ask questions like, what are they made of? How big are they? How old are they? How distant? How far away? How are they powered? And where do they live? And who are their friends? And of course, what's their favorite movie? Now to answer these questions, we're going to start by looking at their spectra. Now, in a spectral line, we have these emission lines, and they're due to an excess of photons at particular wavelengths. Now, bound electrons in an atom can only absorb or emit photons at particular wavelengths, and those are determined by the atom itself, its configuration of charges. And when an ionized atom captures an electron, that electron wants to cascade its way down to the lowest possible energy state that it can occupy. In the case of hydrogen, when ionized hydrogen captures an electron, that electron wants to work its way down, and about 2/3 of the time, it'll emit a Lyman-alpha photon. Now, Lyman-alpha is just the name that we give to a photon of wavelength about 1215 angstroms. It's just a color, like red or blue, but it's often the ultraviolet, so its wavelength is too short for us to see with our eyes. Now, when we look out at the Lyman-alpha blobs, we see, as you would expect, a very strong Lyman-alpha line. And we also see a few other lines from hydrogen, H-alpha, H-beta, and some helium. And if we look into the galaxies that the blobs are enveloping, we'll also pick up some heavier metals, carbon and oxygen. But the Lyman-alpha blobs themselves are composed only of pristine hydrogen and some helium, those elements that were originally made in the Big Bang. Now, what powers the Lyman-alpha emission? Well, as we just discussed, in order to get Lyman-alpha radiation, we need a lot of hydrogen that can be ionized and then cooled so it can recombine and emit Lyman-alpha. In the case of Lyman-alpha blobs, there are two primary energy sources. The first is from internal heating from the galaxies that are contained within the blobs. Now, these galaxies are typically young. They're forming stars at a fairly prodigious rate. And a small fraction of those stars will be these giant O-type stars. And I'm sorry, that's at the very bottom. For those in the back, you may not be able to see it. But the O-type stars are enormous. They're very hot. They're massively bright. And a fair amount of their radiation, almost most of their radiation, is emitted in the higher bands, in UV and higher, and contains plenty of energy to completely ionize hydrogen. Also, and if you were here last month, we talked about quasars. Some of these galaxies contain quasars, and those quasars are essentially black holes with accretion disks if they're feeding. And those disks get very hot, and they also emit massive amounts of radiation in the higher bands, in the UV and in the X-ray. And these two sources push these photons out into the cloud and completely ionize the hydrogen. And as you move a little further away from that radiation, the hydrogen can cool a bit and recombine and emit Lyman-alpha. Now, the second power source we get are from, and let's see if this laser works, are from these cold streams of gas that come flowing in from outside the blob and slam into the gas that's already in there. And they can physically knock electrons free from the atoms. Now, as that gas disperses and cools, again, the hydrogen can recombine and emit Lyman-alpha photons. Now, hydrogen loves Lyman-alpha. And so as these photons are streaming around inside the cloud, neutral hydrogen will pick up those Lyman-alpha photons and will bump their electron up to the first excited state, which is not very stable, and a fraction of a second later will emit that photon again in another direction. So these Lyman-alpha photons scatter about the cloud all kinds of different directions, but eventually they'll work their way out to the edges of the cloud and escape and stream to us, where we'll pick them up some billions of years later. In any case, neither one of these methods alone provides enough energy to represent what we see in these Lyman-alpha blobs, so they're most likely powered by a combination of both of these mechanisms. Now, where do they live and how many of them are there? We find Lyman-alpha blobs in the densest regions of the universe, where we have a lot of galaxies that are forming, they're merging, and they're turning into what will be giant galaxy clusters and superclusters. And we don't find all that many of them. To date, we found a few hundred or so these Lyman-alpha blobs, and given the volume of sky that's been surveyed, that means they're fairly rare. And typically we'll interpret that rarity as meaning they're essentially very short-lived. Now, how old and how big are they? Well, as we said, the principal identifier here is that they have a strong Lyman-alpha emission. And since we know the rest wavelength of Lyman-alpha at about 1215 angstroms, we can measure where we see Lyman-alpha when we look at these galaxies. Now, as you know, the universe is expanding, and as it expands, it stretches the photons along with it. And by measuring where we see the emission lines now, we can see how much the universe has expanded since the time that those photons were emitted. And from that, we can get a rough age. And from that, we can get a distance to these objects. And from that distance, we can get a measure of their size, with their angular dimension on sky. Now, how big are they? Well, individual little knots of Lyman-alpha blobs can be tens of thousands to hundreds of thousands of light years across. But they tend to come together in these sort of amoeba-like shapes that can be hundreds of millions of light years across. And that makes them some of the biggest objects in the universe, bigger even than some of the super galaxy clusters that we see today. When did they first appear? Well, about a few years ago in 2009, Masami Ouchi found the oldest Lyman-alpha blob to date, and he named it Himiko. So finally we have a name that has a little panache to it. Instead of Lyman-alpha blob, 312. Himiko, by the way, is named for a 3rd century Japanese queen who may or may not have had magic powers. It is the oldest, most distant known Lyman-alpha blob at about a redshift of 6.6. That makes it a little less than 13 billion years old and formed about 800 million years after the Big Bang. It's fairly large, 55,000 light years across, and a mass of about 40 billion times the mass of the Sun. So it's not the largest Lyman-alpha blob by any measure, but for its time, it's enormous. About 10 times larger than anything else we see at this redshift. And we thought that could be a problem. There's just not enough time for something that massive to form that soon after the Big Bang. Now, fortunately, or perhaps disappointingly, follow-up observations in 2013 with higher resolution instruments have shown that Himiko is not actually a single Lyman-alpha blob, but is 3 separate blobs that could be in the early stages of merger. Now, where did they go? Well, looking for Lyman-alpha blobs in the nearer by universe presents a new challenge. Now, despite the fact that you can get a very nasty sunburn, our atmosphere does a very good job of blocking out UV radiation. And at a redshift of less than about 2, Lyman-alpha is still in this UV band. So if you want to look for Lyman-alpha objects nearer by, you basically need to get above the atmosphere. And in 2013, a team did just that using the GALEX Space Telescope. They surveyed a number of relatively nearby galaxy clusters at a redshift of about 0.8 and found no evidence of Lyman-alpha blobs, suggesting that by the time the universe is about a third of its current age, the Lyman-alpha blobs had largely disappeared. However, just a few years later, another team, also using GALEX, looked in low-density regions of the universe and found a little over a dozen Lyman-alpha blobs at a redshift of 0.3. So that makes them only about 3.5 billion years old. Now, these nearer-by blobs are a bit different from their brothers. Again, we don't see them in these very dense regions. We see them in the very low-dense regions. And they don't have these cold flows of gas powering the emission. They appear to be powered solely by bursty star formation in some of these AGNs from the few galaxies that they may happen to contain. They're a bit smaller, and because of this late formation, they suggest that they might actually be a second generation of Lyman-alpha blobs. So let's sum up just a little bit and talk about what do we actually know. Well, we know they're mostly composed of pristine hydrogen gas, a little bit of helium, the elements that were made directly from the Big Bang. We know they shine due to a combination of ionizing photons from the galaxies that are embedded within them and from infalling streams of cold gas from the outside. They are mostly found around protogalactic clusters and these very dense regions where lots of galaxies are forming, surrounding these young galaxies. They're really big, hundreds of thousands to hundreds of millions of light years across. They appear not too long after the first galaxies start to form. And in the high-density regions, they start disappearing not too long after star formation has peaked and is starting to slow down. And of course, in the low-density regions, they may appear a lot later, but this may be a separate family from their bigger brothers. So what are they? Well, essentially, they're the remnants of the original matter from the Big Bang. They're a fuel source for star formation in young galaxies. Radiation from these young galaxies puff up the blobs. They blow bubbles in them. And as the fuel, the gas in the blobs is consumed, the blobs thin out. They are unable to cool. They become completely ionized, and they fade into the intergalactic medium, which is essentially transparent, and they disappear from the universe. In a word, they're cosmic baby food powered by baby galaxy burps. Or if you prefer something a little more poetic, they're the intergalactic equivalent of the pillars of creation. But instead of forming individual stars, Lyman-alpha blobs are the host site for the birth of entire galaxies and galaxy clusters. But to say that we really understand Lyman-alpha blobs is a bit of an overreach. There's far more that we don't know than we do. And it's very likely that some of the things we think we know are probably wrong. Now, these are just some of the questions, and I'm not going to go over them. But further study can teach us a lot more about not just the blobs, but how they impact the universe around them and how they've led to the universe we see in front of us. And if you take nothing else from this, remember that maybe Lyman-alpha blobs are around just to remind us that the universe is a really weird place. And you never know what you're going to find if you just keep looking. Thank you.
Thank you, Lyman Z. Coconut. We have plenty of time for questions. Oh, he explained it so well. Anyone? Oh,
down here.
What?
Oh, up there, sorry.
Staircase. Let's do it.
So he's asking that in the talk we said that Lyman-alpha blobs are at the host site of galaxy formations, and does that correlate with where we see dark matter clumping? And the answer is yes. Basically, in one of the earlier slides, and I guess I can back up to one of them here. In the background, eventually we'll get there. Here we go, almost. Here we go. So this is actually an image from a simulation that shows the mass, how matter is clumping in the universe, and this is probably at a redshift around about 2. But yes, exactly. We see these Lyman-alpha blobs, and what we would suggest are these nodes. Advancing here, so in these tight little regions here, which traces where the dark matter halos have collapsed, and they're pulling in this gas.
Yes.
So you said that after a certain amount of time, they start to disappear, and we don't see them. But what are they disappearing? I mean, obviously, it has to. The matter has to.
Right. Oh, so this is a question about how they disappear and kind of maybe when. So the Lyman-alpha blobs themselves, being composed primarily of hydrogen gas, it's that gas that's fueling the star formation in these galaxies. So that gas gets used up as these stars are being created. So that's where part of it goes. It's trapped in these stars, and then of course the stars detonate and blow heavier metals back in the universe. But some of the gas does remain. It just becomes thin and ionized, and thin to the point that it cannot cool down. So when it becomes ionized, it's essentially transparent, and we just don't see them anymore. The remnants are still there, but it's you just can't see it anymore.
Yes, sir.
Sure. So James Webb is looking out not strictly for Lyman-alpha blobs, although it will be able to see them. It's going to be focused in these early formation of galaxies. So it's looking back even further than we would normally expect to see the Lyman-alpha blobs. Although certainly, given its eye, it should be able to see maybe fainter ones, maybe closer to their demise into the IGM.
Yeah, right there.
Given the current information that you currently have, are you able to predict where a Lyman-alpha blob might appear, or?
Sure. So the question is about predicting where we would find them. Again, there aren't that very many of them, but we do find them in these dense regions of rapidly forming galaxies and these protoclusters. And so that's where we look. And we had that survey in 2013 that went looking for them in those regions and found that they had disappeared. So because it draws in matter into these deep gravity wells, the place to look for them is in the protoclusters of galaxies, and the time frame to look for them is a redshift roughly 2 to 4 or 6 or so.
And last question.
Right.
So ionized hydrogen means that there's been enough energy imparted on it that the electron is stripped away. So now you have a proton that's heated up, and then what? It gets separated in the vacuum of space such that it has no place to radiate its heat to. It's hot but trapped.
Kind of. So the question is about why is it that as these age and become thin, they cannot cool down, right? So we have these photons that are still coming out of the galaxies, and they strip away the electrons from the hydrogen and ionize it. Now, when the clouds are dense, the cloud itself can sort of self-shield and protect further away hydrogen from these incoming photons, and so they can cool around those boundaries and recombine. As that fuel is used up, the cloud becomes too thin, and these photons are still coming out, and so there's really no chance, there's not that much hydrogen left, and there's no chance the photons overwhelm it, and the naked protons cannot really recombine with the electrons.
Well, that was great. Thank you, Lyman Z. Coconut.